Modern LLMs are massive, containing billions of parameters. Storing these weights in standard 16-bit floating-point format requires astronomical amounts of GPU memory. A 70 billion parameter model needs 140 gigabytes of VRAM just to load, completely out of reach for consumer-grade hardware. This memory bottleneck is the precision crisis. To run these models efficiently, we must reduce the bits used per parameter. Enter quantization, the process of mapping high-precision continuous weight values to low-precision discrete integers. But naive quantization destroys accuracy. How do we compress a model's brain to 4 bits or even lower without losing its intelligence? The answer lies in hardware-aware, mathematically rigorous quantization frameworks. The foundation of compression is uniform linear quantization. We map floating point weights to low-bit integers like int4 or int8 using a scaling factor, s, and a 0-point z. The math is simple. The quantized weight equals the round of the float weight divided by s plus z. Dequantization reverses this, approximating the original value. However, neural networks contain activation outliers, highly critical feature channels with values up to 100 times larger than average. Naive quantization scales the entire tensor to accommodate these outliers, crushing the resolution of normal weights. To preserve intelligence, we cannot treat all parameters equally. We must either isolate these outlier activations or dynamically adjust weight scales to protect them. Activation-aware weight quantization, or AWQ, solves the outlier problem elegantly. Instead of quantizing outliers and normal weights uniformly, AWQ recognizes that only a tiny fraction of weights, about 1%, are highly sensitive to activation magnitude. To protect these critical weights, we scale them up by a factor, s, before quantization, and scale down the activations correspondingly to maintain mathematical equivalence. AWQ searches for the optimal per-channel scaling factor by minimizing the reconstruction error of the layer output. By shifting the precision burden from the weights to the activation scaling, AWQ achieves robust 4-bit quantization with virtually zero loss in model perplexity, keeping execution highly hardware-friendly. While AWQ uses activation statistics to risk-scale weights, GPTQ takes an analytical error minimization approach. Based on the optimal brain surgeon framework, GPTQ quantizes weights column by column while updating the remaining unquantized weights to compensate for the introduced error. The mathematical engine of GPTQ is the Hessian matrix of the layer input, which represents the second-order sensitivity of the loss. By computing the inverse Hessian, GPTQ determines exactly how to adjust the unquantized weights to minimize the output reconstruction error. GPTQ processes weights in blocks, using lazy batching and Cholesky decomposition to achieve extremely fast, highly accurate 4-bit quantization for 100 billion parameter models in just a few hours. With weights successfully quantized, how do we deploy them across diverse hardware? This is the domain of GGUF, a single-file format designed for fast loading and seamless deployment. Unlike older formats, GGUF embeds all metadata, hyperparameters, and vocabulary directly within the model file, preventing version mismatch. More importantly, GGUF is optimized for CPU-GPU co-design, enabling split computation. It partitions quantized weight blocks across VRAM and system memory, allowing consumer machines with modest GPUs to offload heavy operations while using the CPU and system RAM for the rest. For more deep dives into the software and hardware architectures of AI, subscribe to Gemini 3.5 Flash Model. Let's keep optimizing the future of computation.